Our second semester of chemistry starts with an introduction to the mole and molar mass. First, we'll meet your new sidekick, the mole. Then we'll look at our map and see how the mole changes it. We'll define molar mass, and finally we'll do some practice problems. Many heroes have a sidekick. Yours is going to be the mole. Alright, so as we started our presentation, I asked students to draw a mole. So I'm going to go ahead and draw a little mole here, poking its head out of the ground. And moles kind of have these interesting little mouths, like that. Alright, so there's my little mole. The first thing we did in class is watch a video from TED Education about the mole as a number. If you were not in class or would like to rewatch that video, it's posted as the first thing in Schoology. But essentially the video described the mole as a number. So kind of like a conversion factor. So we know that 1 dozen equals 12. Like we have 1 dozen eggs is 12 eggs. We know that a pair of something is 2. The mole instead stands for a number, which is 6.02 times 10 to the 23rd. The mole is defined as the number of atoms in 12 grams of carbon-12, which does come out to more exactly 6.0221421 times 10 to the 23rd. When we call this number Avogadro's number. Amedeo Avogadro, though, did not actually calculate this number. That was years later by a man called Johann Loschmidt. Avogadro, on the other hand, is most well known for postulating that an equal volume of 2 gases under the same temperature and pressure will contain the same number of molecules. And it's that principle as to why this works, where 1 mole of any element will contain Avogadro's number, 6.02 times 10 to the 23rd, number of atoms. The main way we're going to use Avogadro's number in chemistry class is as a conversion factor. We'll be using Avogadro's number when we want to change from atoms to moles of any element, because 1 mole of any element is 6.022 times 10 to the 23rd atoms. You can also use it in reverse. Back at the beginning of the year, we used conversion factors to work problems. Some of the conversion factors we use are listed here below. Other ones you might already be familiar with, such as that 1 foot equals 12 inches, 1 dozen equals 12, 60 seconds equals 1 minute. We use conversion factors whenever we want to change from one unit to another. Think of that word conversion. It's got the root word convert. Other words that have convert in them, think of like a convertible car. It changes from having a roof to not having a roof. So it's changing the substance of it, but it's still at the end of the day a car. So even though we're changing the units on these conversion factor problems, it still represents that initial value. So just like those conversion factors from the last slide, we can use Avogadro's number to change from atoms to moles and from moles to atoms. So if we have 3.5 moles of carbon, how many atoms would we have? We'll have to use our new conversion factor that 1 mole of any element equals 6.02 times 10 to the 23rd atoms. So what would we need to do to those two numbers? Since we know that 1 mole of any element is 6.02 times 10 to the 23rd atoms, we'd multiply that by 3.5 to give a total answer of 2.107 times 10 to the 24th atoms. Before we get much farther, we'll need to have a map. As you probably guessed, our map is the periodic table. Before using the periodic table today, let's remind ourselves how to use it. There are 2 main numbers for each element on the periodic table. For carbon, those are listed here. The one at the top, 6, is its atomic number, and the one at the bottom, 12.011, is its atomic mass. What do these mean? So during class, I asked students, what do we already know about carbon based on it having an atomic number of 6? Many students remember that this refers to the number of protons, which is correct. So carbon would have 6 protons. In the situation of a neutral atom, one that does not have a charge, this atomic number also corresponds to the number of electrons. So if we've got 6 protons and it's a neutral atom, no charge, then we'd also have 6 electrons. Then I asked students, what do we know about carbon based on it having an atomic mass of 12.011? This was a bit trickier. We didn't use atomic mass so much last semester. But then we remembered that we could find the number of neutrons by subtracting the atomic number from the atomic mass. That's because the atomic mass corresponds to the mass of the atom, which is our protons, our neutrons, and electrons. Because electrons are so small, though, we really only include the protons and neutrons in the calculation for atomic mass. Since we know the number of protons, 6 for the atomic number, we can subtract that from the atomic mass to get the number of neutrons. Part of the reason why it's a decimal point number is because the atomic mass is an average. So there are multiple different versions of an atom. We call those isotopes that have different number of neutrons. So that atomic mass is a representation of a weighted average. Here's a Bohr model of the carbon atom, which shows all the information that we could glean from those 2 numbers on the periodic table. We can see the 6 protons from the atomic number. Since it's a neutral atom, that also corresponds to the 6 electrons. And finally, we can see the 6 neutrons, the difference between the atomic mass of 12.011 minus the atomic number of 6. But wait! Here comes our mole sidekick to change everything up. Now when we look at the periodic table, I want you to think about molar mass. Molar mass is defined as the mass in grams of 1 mole of any substance, and it happens to be equal to the atomic mass. So if we want the mass of 1 mole, we'll look on the periodic table at the atomic mass. We simply add a letter G to indicate that it's grams, and then we call that the molar mass. So let's use the periodic table to determine which would have a higher mass. Would it be 1 mole of hydrogen or 1 mole of oxygen? When we look at the periodic table, we can see that hydrogen has an atomic mass of 1.008. That means it's the same as its molar mass. So if we had 1 mole of hydrogen, it would have a mass of 1.008 grams. Meanwhile, oxygen's atomic mass is 15.999 grams. So if we had 1 mole of oxygen, it would have a mass of 15.999 grams. 15.999 is more than 1.008, so therefore 1 mole of oxygen has more mass. Which would contain more atoms, though? Would 1 mole of hydrogen contain more atoms or 1 mole of oxygen? What do you think? That's a bit of a trick question because they would both have the same number of atoms, which is Avogadro's number. 6.022 times 10 to the 23rd atoms. So even though 1 mole of hydrogen and oxygen have a different mass, they still have the same number of atoms or particles. And we can think of that because if we remember back to atomic radius, oxygen and hydrogen would have different atomic radii. They're simply different sizes. Moving forward, we're going to be using molar mass as a conversion factor, just like we used Avogadro's number. So we'll use this as a way to change between moles and now mass. And we can do this because 1 mole of a substance is always equal to its atomic mass. So for example, we'll look at the periodic table and we can see that 1 mole of gold would have a molar mass of 197 grams. So that means if we have 197 grams of gold, we know we have a mole of gold. So we can use this to work similar problems. I'm going to do a few examples for you here in this video, but I'm going to do the examples from the homework quiz and post those separately. For this example, we'll look at how many grams are in a sample containing 5.73 moles of helium. So we'll look for our given. That's usually the information with a number. And I see we've got 5.73 moles of helium. So that's what I'm going to go ahead and write first. 5.73 moles of helium. Helium is abbreviated He on the periodic table. So now I'll read my question again. How many grams are in a sample containing 5.73 moles of helium? And I'll see that my problem is asking for how many grams. So that's where I'm trying to end up. So I'm going to go ahead and write that down, that my goal is grams. So I'm at moles, and I know I want to get to grams. Do I have a relationship in a unit conversion factor that I could use to get from moles to grams? I do. That's called molar mass. So we're going to go ahead and look at our periodic table to find the molar mass of helium. Zoom in a bit for you there, but it is listed at 4.002602. We're going to go ahead and call that 4. So that means that our conversion factor would be that 4.00 grams of helium equals 1 mole. That's the relationship between atomic mass and the mole on the periodic table. So we'll set up the rest of our problem and see where we need to put this information. So we started off with moles of helium. So in order for us to end up with grams, we're going to need to divide by moles of helium. So we'll go ahead and put 1 mole of helium on the bottom so that those two can cancel out. Moles of helium will cancel with moles of helium. Now we'll put the other part of our conversion factor, what it equals, right above it. 4.00 grams of helium. And we do that because with a conversion factor, our problem will still be the same as long as we're multiplying by something where the top equals the bottom. The only thing that we're changing is the units. So we have 4 grams of helium equals 1 mole of helium. And now we'll look at our problem and we see that, yes, we've canceled out our moles of helium because it's on the top and the bottom. And now all that's left is grams of helium, which is what we're trying to solve for. When we do these problems, we want to multiply by anything that's on the top and divide by anything that's on the bottom. So I'm going to take 5.73, multiply it by 4.0, and then I don't have to divide by 1 because anything divided by 1 is itself. So I will type in on my calculator 5.73. Oh, I have a wrong number. It's something that I always say to be mindful of, is typing things in on the calculator wrong. 5.73 times 4, and that gives me 22.92 grams of helium. All right, so other people want to conceptualize this a little bit different, so I want to show you another way to solve this problem if it makes it a little bit easier. So instead of setting it up like this, you can also look at this conversion factor and say, I've got 4 grams of helium in 1 mole, but I've got 5.73 moles. So therefore, how many grams are in that? And now you can solve for x by setting up a proportion problem. So you can do 1 mole over 4 grams. That's your first relationship here. Equals, make sure to set it up correctly on the same side, so 5.73 moles over x. And now with this type of problem, you can cross multiply to get x times 1 mole equals 5.73 moles times 4.0 grams. Now we'll divide by 1 mole on this side because we need to get x by itself. When we do that, cancel that out. And now X equals 5.73 moles times 4 grams divided by moles. We'll see that these moles will also cancel out. And it's exactly what we've written here. 5.73 times 4 divided by 1. So 2 different ways to solve the problem. When our problems start getting longer and longer, though, this way will save you a little bit of time because you can solve them just a bit faster. For this next one, let's look at how many moles are in a 178.9 gram sample of magnesium. So first we'll find our given. That's the information that the problem has given us. And it says we've got 178.9, that's grams of magnesium. All right, so then we'll read the problem again and find out what we're asking for. So it says how many moles are in. So we are looking for moles. That's where we're trying to end up. So I've got 178.9 grams of magnesium, and we're trying to end up with moles. So we need to find a relationship between grams and moles. Luckily, that's what molar mass tells us. So molar mass is the mass of 1 mole, and it is the same as the atomic mass, but expressed in grams. So we'll look at our periodic table, find magnesium. Magnesium's over here. It says it's got a atomic mass of 24.3050, which should be its molar mass. So we'll write that number down, 24.305. And now we put it in grams, and we know that that equals then 1 mole of magnesium. So that's the relationship we're going to need to solve this problem. Again, we get that number from the periodic table. It's the atomic mass, the one that has the decimal points, 24.305. All right, so we'll set up our problem now. We've got grams of magnesium as our first unit. So that means in order to cancel that out, we're going to need to put grams of magnesium here. So we put grams of magnesium. We then look for the number from the conversion factor. We've got 24.305. And on top, we list what it equals, which is 1 mole of magnesium. And now our units will cancel out because we have grams of magnesium on the top and grams of magnesium on the bottom. That means that we are left with moles, which is the exact unit we're trying to end up with. So that's going to work out for us. All right, so now we're ready to solve our problem. As we solve these problems, we know we're going to have to multiply by anything on the top and divide by anything on the bottom. So I'll go ahead and grab my calculator. And I've got 178.9. I don't need to multiply by the 1 because anything times itself is itself. But I will then divide by 24.305. And that gives me 7.361. And that's now expressed in moles. That's moles of magnesium. Okay. All right, so the other way of working this problem, if you were to set it up as a proportion problem instead, is that you'd say you have 178.9 grams of magnesium. So we know that 24.3050 grams is 1 mole, but we have 178.9. So that would equal X. And then we can set it up like a proportion problem, where we have 1 mole equals 24.305. And then we have X, 178.9. As you're setting this up, you need to make sure that these are your units match across that way. So this is moles and moles, grams and grams, and now we will cross multiply. So we can cross multiply, and therefore we will end up with X times 1 mole of magnesium magnesium equals, the other part, 24.305 grams. Oh, I put my X on the wrong spot. Sorry. 1 mole magnesium, 178.9 grams is over here. 24.305 grams X. And then we'll want to divide by 24.305 grams on both sides. And therefore these will cancel. We'll be left with X equals 178.9 times 1 mole over 24.305 grams, which is exactly what we've written right up here. So it'll give us the exact same answer. So 2 different ways to solve it. I think going straight to this is a bit easier, especially long term. All right, so now we'll look at this question that asks how many atoms are in 237.5 grams of neon. So we'll look for our given. And we see that we've got 237.5 grams of neon. So we'll go ahead and write that down. 237.5 grams of neon. Okay. Now I'll read our question again. How many atoms are in? So we need to find atoms. So we'll write that down. That's what we're trying to solve for, is atoms. Okay. All right. So to get from grams to atoms, we don't have a relationship that goes directly there. Instead, we're going to have to go through the mole. So what is the relationship then instead between, say, grams and moles? So we've started with grams, and we know that we want to end up with moles. So in order to figure out how many grams of neon are in 1 mole of neon, we'll use the periodic table. And we'll look for neon's atomic mass, which is 20.1797. So that means 20.1797 grams of neon is the same as 1 mole of neon. And that's due to the rule of molar mass and the relationship between the mole and the periodic table. So when we're plugging this into our problem above, we'll want to set it up in a way that we've got grams of neon canceling out. Because we had grams of neon at the top, and we need it to cancel out so that we can move forward to atoms. So we're going to go ahead and list the molar mass of neon right there. And we know that this equals 1 mole. That's our relationship, is that many grams equals 1 mole of neon. So we'll write that on the top. And now we will go ahead and cross out those units. Grams of neon cancels with grams of neon. And now we've got moles of neon. We're still not done though, because we're trying to get all the way to atoms. So now we need a relationship between moles and atoms. So we have to think on what is that relationship between moles and atoms. So if we've got 1 mole of neon, how many atoms is it? And that's Avogadro's number, which is 6.02 times 10 to the 23rd. And that is in atoms. So we'll use that last conversion factor here. So we've got 1 mole of neon on the top. In order for it to cancel out, we're going to put in moles on the bottom and what it equals on the top. And now our problem does end in atoms, which is exactly what we were trying to solve for. It's atoms. So now we know that if we multiply or divide across, that this will give us our answer. So with these problems, we have to multiply by anything on the top and divide by anything on the bottom. So when working these, especially ones that do have Avogadro's number on the top, I often do like to plug Avogadro's number into my calculator first. If you choose not to, the other way would be maybe put it in parentheses. That means making sure that it's separated out here. So we could write 237.5 grams. We don't need to write the units because, again, those have canceled. times Avogadro's number, which I am going to put in parentheses. And then I'm going to divide the whole thing by 20.1797. And that's going to give me a number of 7.085 times 10 to the 24th atoms. And that would be how I would write it per scientific notation. I've not been super picky on scientific notation yet, but we would want to make the units match, or the number of digits match. All right, so that is how we would work this problem. Multiple conversion factors needed to solve this problem. When we have these long problems going from grams to atoms, it's important to note that we have to go through the mole. Going to the mole is generally a good first stepping point. Sometimes you'll need to find the molar mass of a compound or molecule. So that's something that's not on the periodic table, like salt, which is sodium chloride. So it's two or more elements stuck together. So in order to find the molar mass of compounds and molecules, you'll need to first look up the molar masses of each individual element. Then we've got to multiply the molar mass by the subscripts of each. And finally, we'll add those molar masses together. I've done an example for you that I'll show next. All right, so here's an example we will work that is a compound composed of two polyatomic ions. That's ammonium carbonate. So in this compound, we actually have two of the ammonium ion and one carbonate ion, which are bonded together. So in order to figure out how many grams of ammonium carbonate we have in 3 moles, we're going to need to calculate the molar mass of ammonium carbonate. So that means we need to discover our own conversion factor. So we'll look at the formula and the subscripts to determine how many of each atom needs to be considered in the molar mass formula. So we've got 1 nitrogen, but then it gets multiplied by 2 based on the subscript. We have 4 hydrogens, but they're multiplied by 2, so that becomes 8. There's 1 carbon, and there's 3 oxygen. Okay, so now we can use our periodic table to look up the atomic mass, okay, the molar mass. I'm going to use some approximations for this example right now. So I know that nitrogen is roughly 14, so 14 times 2 would be 28. I know hydrogen is roughly 1, so 1 times 8 is 8. Carbon is 12, and oxygen is 16, so times 3 is 48. So if we add all that up, that becomes 96. So we express that in grams per mole. 96 grams per mole. So now we have that number, and that can be plugged into our conversion factor. So we've got 96 grams. So we've got 3 moles of ammonium carbonate, and now we know that 1 mole equals 96 grams. So we'll go ahead and plug this into our equation, putting the moles on the bottom so that they'll cancel out. And then the grams on the top. And now we'll multiply across 3 times 96. And I get 288 grams. So there is another way that you can add up the molar mass of compounds. You could look at it as 2 separate polyatomic ions and add that first. So you can see that nitrogen's 14, hydrogen's roughly 1, so that would be 18, and then multiply that times 2 because there's a 2 in the formula. And then look at carbonate, which is 12 plus the 3 oxygens, because that does 60, and then add the 2 different ions together, so 36 plus 60 would be 96. So 2 different ways that you can solve this to add up molar mass before using that molar mass to solve your equation. At this point, some of you may be wanting to rethink your sidekick. but the mole is here to stay. Like any lovable sidekick, he can be annoying at best and downright impossible to work with at worst. But on the very best of days, the two of you can make amazing discoveries and change the world.